All right, and welcome back, starting out lecture 2, or part 2 of chapter 10. So, half-lives and time constants. A useful indication of the rate of a first-order chemical reaction is the half-life, or T1/2, of a reactant, which is the time it takes for the concentration of the species to fall to half its initial value. We can find the half-life of a species, A, that decays in first-order reaction, related to equation 1014, by substituting the concentration of A equals 1/2 the concentration of initial concentration of A. Then T equals T1/2. And we can therefore create the following. So that when we rearrange, we can just say for first order reactions that the half-life, or time to reach the concentration of half the initial value, equals the natural log of 2 divided by K. This is a fairly straightforward thing we've done quite a bit at the end of second semester Gen Chem, but it's worth revisiting. Also take a note, figure 1013, where you can see the molar concentrations of N2O5 after a succession of half-lives. The main point to note about equation 1016 is that for a first-order reaction, the half-life of a reactant is independent of its concentration. It follows that if a concentration of A at some arbitrary stage of the reaction is A, then the concentration will fall to 1/2 A after an interval of natural log 2 divided by K, whatever the actual value of A may have been. Some half-lives are given in table 10.2. Now, in contrast to first-order reactions, the half-life of a second-order reaction does depend on the concentration of the reactant, and lengthens as the concentration of reactant falls. It's therefore not characteristic of the reaction itself, and for that reason is rarely used. We can use the half-life of a substance to recognize first-order reactions. All we need to do is inspect a set of data of composition against time. If we see that the initial concentration falls to half its value in a certain time, and that another concentration falls to half its value in the same time, then we can infer that the reaction is first order. The first order character can then be confirmed by plotting the natural log of the concentration of A against time and obtaining a straight line as indicated earlier. Another indication of the rate of a first-order reaction is the time constant, the time required for the concentration of a reaction to fall to 1/E of its initial value. From equation 1015a, it follows that the rate constant times the time constant equals the natural log of E equals 1. Therefore, the time constant is simply the reciprocal of the rate constant, and that's shown in equation 1017, which I've just checked. Now, we mentioned at the very beginning that there was a temperature dependence on rate reaction, so let's talk about that further. The rates of most chemical reactions increase as the temperature is raised, but many organic reactions in solution lie somewhere in the range spanned by the hydrolysis of methyl ethanoate, for which the rate constant at 35 degrees is 1.8 times that at 25 degrees, and the hydrolysis of sucrose, for which there's a factor of 4.1. Enzyme-catalyzed reactions may show more complex temperature dependence because raising the temperature may provoke conformational changes that lower the effectiveness of the enzyme. So this doesn't necessarily apply in enzyme-related reactions. Indeed, one of the reasons why we fight infection with a fever is to upset the balance of reaction rates in the infected organism and hence destroy it by the increase in temperature. There's a fine line, though, because between killing the invader and killing, the invaded or us. So let's start out discussing the Arrhenius parameters. As data on reaction rates were accumulated towards the end of the 19th century, the Swedish chemist Svante Arrhenius noted that almost all of them showed a similar dependence on the temperature. In particular, he noted that a graph of a natural log of K, where K is the rate constant for the reaction, against 1/T, where T is the absolute temperature, at which K is measured gives a straight line with a slope that is characteristic of the reaction. The mathematical expression of this conclusion is that the rate constant varies with temperature such that the natural log of the rate constant equals an intercept plus a slope times 1 over t. This expression is normally simply written as the Arrhenius equation, equation 1018, where the natural log of K equals the natural log of species A minus E sub A over RT. Or alternatively, it can be arranged as follows, as I just underlined, and taking antilog e to the x on both sides so that it can be expressed as in equation 1019. The parameter A, which is has the same units as K sub R, is called the pre-exponential factor. And E sub A, which is a molar energy and normally expressed in kilojoules per mole, is called the activation energy. Collectively, A and activation energy are called Arrhenius parameters of the reaction. And we're taking a look at that on table 5 here. Now, a practical point to note from equation 1019 and illustrated in figure 1016 below is that a high activation energy corresponds to a reaction rate that is very sensitive to temperature. The Arrhenius plot has a steep slope meaning. Conversely, a small activation energy indicates a reaction rate that varies only slightly with temperature. The slope is shallow. A reaction with zero activation energy, such as for some radical recombination reactions in the gas phase, has a rate that's largely independent of temperature. Now, once the activation energy of a reaction is known, it is a simple matter to predict the value of a rate constant, K, at temperature T prime, for its value, K, at another temperature T. To do so, we can write the following, where the natural log of the reaction rate at temperature T prime equals the natural log of A minus the activation energy over R over T prime. We can also relate those for temperatures that are not at T prime. And then we subtract the second from the first, giving us the following, which can be arranged to the expression in equation 1020. This allows us to calculate K at different temperatures if we know all of the factors associated with K at T prime. And there's a brief illustration of how that might work below. Now, here's a more detailed example, which I encourage everybody to pause the video, take your time, work through example 10.3, determining Arrhenius parameters from the data set. And once you've done that, we'll pick up the lecture with the next slide. Now that we've completed that example, moving on to some of the underlying rationale associated with kinetics, specifically collision theory. We can understand the origin of the Arrhenius parameter most simply by considering a class of gas phase reactions in which reaction occurs when two molecules meet. That is, in the terminology to be introduced in section 11.13, our following chapter, we are considering bimolecular gas phase reactions. In this collision theory of reaction rates, it is supposed that reaction occurs only if two molecules collide with a certain minimum kinetic energy along their line of approach, meaning they have to have sufficient kinetic energy and they have to have appropriate orientation upon collision. In collision theory, a reaction resembles the collision of two defective billiard balls. The balls bounce apart if they collide only with only a small energy, but might smash each other into fragments or products if they collide with more than a certain minimum kinetic energy. This model of reaction is reasonable first approximation to the types of processes that take place in planetary atmospheres and govern their composition and temperature profiles. A reaction profile in collision theory is a graph showing the variation in potential energy as one reactant molecule approaches another, and the products then separate, and this is shown in figure 1019 below. On the left, the horizontal line represents the potential energy of the two reactant molecules that are far apart from one another. The potential energy rises from this value only when the separation of the molecules is so small that they're actually in contact. When it rises as bonds bend and start to break. The potential energy reaches a peak when the two molecules are highly distorted. Then it starts to decrease as the bonds are formed. At separations to the right of the maximum, the potential energy rapidly falls to a low value as the product molecules separate. For the reactions to be successful, the reactant molecules must approach with sufficient kinetic energy along their line of approach to carry them over the activation barrier, the peak in the reaction profile. As we'll see, we can identify the height of the activation barrier with the activation energy of the reaction. With the reaction profile in mind, it's quite easy to establish that collision theory accounts for Arrhenius behavior. Thus, collision frequency, the rate of collisions between species A and B, is proportional to both their concentrations. If the concentration of B is doubled, then the rate at which A molecules collide with B is also doubled. And if the concentration of A is doubled, then the rate at which B molecules collide with A is also doubled. It follows that the collision frequency of A and B molecules is directly proportional to the concentrations of A and B, and we can simply write that collision frequency is proportional to the concentration of A times the concentration of B. Now, next, we need to multiply the collision frequency by a factor f that represents the fraction of collisions that occur with at least a kinetic energy, activation energy, along the line of approach, meaning the orientation of the molecules upon collision needs to be appropriate to facilitate the chemical reaction to occur. For only these collisions will lead to the formation of products. Molecules that approach with less than kinetic energy of activation energy will behave like a ball that rolls towards the activation barrier, fails to surmount it, and rolls back to the initial state. We saw in section 1.6 that only small fractions of molecules in gas phase have very high speeds, and that the fraction with very high speeds increases sharply as temperature is raised. Because the kinetic energy increases as the square of the speed, we expect that at higher temperatures, a larger fraction of molecules will have a speed and kinetic energy that exceed the minimum values required for collision that lead to formation of products. The fraction of collisions that occur with at least a kinetic energy of activation energy can be calculated from general arguments developed in Chapter 21 concerning the probability that a molecule has specified energy, which results in the statement F equals E raised to the exponent of negative activation energy over RT. This fraction increases, This fraction increases from 0 when temp equals 0 to 1 when T is infinite, which is absolute temperature. Note figures 1020 and 21. In 1020, we see that the criterion for successful collision is that the two reactant species should collide with a kinetic energy along their line of approach that exceeds a certain minimum value of activation energy. And in 1021, we see a nice reminder of how, according to Maxwell's distribution of speeds, as the temperature increases, so does the fraction of gas phase molecules with a speed that exceeds the minimum value required to exceed a collision activation energy. Now, at this stage, we can conclude that the rate of reaction, which is proportional to the collision frequency multiplied by the fraction of successful collisions, is proportional to the concentration of A times the concentration of B times E raised to the exponent negative activation energy over the gas constant over absolute temperature T. If we compare this expression with the second order rate law, where V equals K times A to the first power and B to the first power, it follows that K should be proportional to E raised to negative EA over RT. This expression has exactly the Arrhenius form if we identify the constant of proportionality as A. Collision theory therefore suggests the following interpretations. 1. The pre-exponential factor A is the constant of proportionality between the concentrations of reactants and the rate at which the reactant molecules collide. And 2. The activation energy is the minimum kinetic energy required for a collision to result in reaction. The value of A can be calculated from the kinetic theory of gases in Chapter 1, shown here, but we've already done this, where m sub A and m sub B are the masses of the molecules of A and B, and omega is the collision cross-section. However, it's often found that the experimental value of A is smaller than the calculated from the kinetic theory. One possible explanation is that not only must the molecules collide with sufficient kinetic energy, but they must also come together in a specific relative orientation. It follows that the reaction rate is proportional to the probability that the encounter occurs in the correct relative orientation. The pre-exponential factor A should therefore include a steric factor, P, which usually lies between 0, where no orientation leads to reaction, no relative orientation leads to reaction, or 1, all relative orientations lead to reaction. As an example, look at the following, in which 2 NaCl molecules collide and break apart into 2 nitrogen monoxide molecules and a chlorine gas molecule. For this example, P is approximately equal to 0.16. For the hydrogen addition reaction, shown below, P is only 1.7 times 10 to the negative 6, which suggests the reaction has very stringent orientation requirements. And a good example of this is when you were doing organic chemistry and you had a scenario where you had a nucleophile attacking a carbonyl, you had to have a backside attack orientation to allow the electrons from the nucleophile to occupy the antibonding orbital behind the carbon so that it could push the electrons from the pi bond up to the oxygen. Without the backside attack, you couldn't do this particular reaction. And this is an example of the steric factor which we're describing here in organic chemistry terms. Now, if we take a look at figure 1022, this reaffirms the fact energy is not the only criteria of a successful reaction, where orientation may also play a role, and we know that it does. Some reactions have a P which is greater than 1. Such a value may seem absurd, but it appears to suggest that the reaction occurs more often than the molecules meet. An example of this kind is as follows, in which a potassium atom plucks a bromine atom out of a bromine molecule. For this reaction, the experimental value for P is 4.1. In this reaction, the distance of approach at which the reaction can occur seems to be considerably larger than the distance needed for deflection of the path of the approaching molecules in a non-reactive collision. To explain the surprising conclusion, it has been proposed that the reaction proceeds by a harpoon mechanism. This brilliant name is based on a model of a reaction that pictures the potassium atom as approaching the bromine molecules, and when the two are close enough, an electron, the harpoon, flips across to the bromine molecule. In place of two neutral particles are now two ions, so there is a Coulombic attraction between them, and this attraction is the line of the harpoon. Under its influence, the ions move together, the line is wound in, the reaction takes place, and potassium bromide and bromide emerge. The harpoon extends the cross-section for the reactive encounter, and we would greatly underestimate the reaction rate if we used for the collision cross-section the value for simple mechanical contact between potassium and bromine gas. So, moving along nicely to transition state theory. There's more sophisticated theory of reaction rates that can be applied to reactions taking place in solution as well as in the gas phase. In the transition state theory, also called the activated complex theory of reaction, it's supposed that as two reactants approach, their potential energy rises and reaches a maximum as illustrated in the reaction profile in figure 1023 to the right. This maximum corresponds to the formation of an activated complex, a cluster of atoms that is poised to pass on to products or to collapse back to reactants from which it was formed. So once we're at an activated complex at the peak, reversibly, it can travel back downhill towards reactants, which are more stable than the activated complex, or towards products, which is ultimately substantially more stable than reactants in this particular example. Initially, only the reactants A and B are present. As the reaction events proceed, A and B come into contact, distort, and begin to exchange or discard atoms. The potential energy rises to a maximum, and the cluster of atoms that correspond to the region close to the maximum is the activated complex. The potential energy falls as the atoms rearrange in the cluster and reaches a value characteristic of the products. The climax of the reaction is at the peak of the potential energy. Here, two reactant molecules have come to such a degree of closeness to distortion that it affects the maximum energy allowed for the system. This crucial configuration that we're describing is classically called the transition state of the reaction. Although some molecules entering the transition state might revert to reactants, if they pass through the configuration, it's probable that products will emerge from the encounter. Now, the reaction coordinate is an indication of the stage reached in this process. On the left, we have undistorted, widely separated reactants, and on the right are the products. Somewhere in the middle is the stage of the reaction corresponding to the formation of the activated complex or transition state. The principal goal of transition state theory is to write an expression for the rate constant by tracking the history of the activated complex from its formation by encounters between the reactant to its decay in products. Here, we outline the steps involved in the calculation with an eye towards gaining insight into molecular events that optimize the rate constant. The activated complex, C, is formed from the reactant A and B, and it is supposed, without much justification, that there is an equilibrium between the concentration of A, B, and C, which is shown below. So for the reaction of A and B forming the transition state C, there would be an equilibria description where C is the product over the two reactants. At the transition state, motion along the reaction coordinate sorry for the quick reset, but I was just interrupted by a small human in the family. So I'm going to pick this back up at the beginning. So at the transition state, motion along the reaction coordinate corresponds to some complicated collective vibration-like motion of all the atoms in the complex and the motion of the solvent molecules if they're involved too. However, it's possible that not every motion along the reaction coordinate takes the complex through the transition state and to the product P. By taking into account the equilibrium between AB and the transition state C and the rate of successive passage of C through the transition state, it's possible to derive the Eyring equation for the rate constant, shown in equation 1023 here, where K equals R over Na equals 1.381 times 10 to the negative 23 joules per Kelvin. It's Boltzmann's constant. And H equals 6.626 times 10 to the negative third joules per second, being Planck's constant. The factor kappa is the transmission coefficient, which takes into account the fact that the activated complex does not always pass through the transition state. In the absence of information to the contrary, the transmission coefficient is assumed to be about 1. The term kt over h in equation 1023, which has the dimension of a frequency, as kt is an energy and division by Planck's constant turns an energy into a frequency, arises from the consideration of the motion of atoms that leads to the decay of C into products as specific bonds are broken and formed. It follows that one way in which an increase in temperature enhances the rate is by causing more vigorous motion in activated complex, facilitating the rearrangement of atoms and the formation of new bonds. Calculation of the equilibrium constant, K, is very difficult except in certain simple model cases. For example, if we suppose that the reactants are two structureless atoms and that the activated complex is a diatomic molecule of bond length r, then K turns out to be the same as for collision theory, provided we interpret the collision cross-section in equation as pi r squared. It's more useful to express the iron equation in terms of thermodynamic parameters and to discuss reactions in terms of their empirical values. We saw in section 7.3 that an equilibrium constant may be expressed in terms of the standard reaction Gibbs energy, negative RT, natural log K, equals delta G. In this context, the Gibbs energy is called the activation Gibbs energy and written as delta G. It follows that the following. Activation Gibbs energy in this case, or change in activation Gibbs energy, equals RT ln K of activation. Therefore, we can write the following for equation 1024, describing delta G, delta H, and T delta S for the activated state. We can conclude that, assuming the transmission coefficient equals 1, kappa equals 1, the following. This expression has the form of the Arrhenius expression in equation 1019. If we identify the enthalpy of activation, delta H, with the activation energy and the term in parentheses, which depends on the entropy of activation, with the pre-exponential factor. And finally, the advantage of transition state theory over collision theory is that it is applicable to reactions in solution as well as gas phase. It also gives some clue to the calculation of the steric factor P for the orientation requirements are carried in the entropy of activation. If there are strict orientation requirements, for example, in the approach of a substrate molecule to an enzyme, then the entropy of activation will be strongly negative, representing a decrease in disorder when the activated complex forms, and the pre-exponential factor will be small. In practice, it's occasionally possible to estimate the sign and magnitude of entropy of activation and hence to estimate the rate constant. The general importance of transition state theory is that it shows that even a complex series of events, not only a collision encounter in the gas phase, displays Arrhenius-like behavior, and that the concept of activation energy is in fact applicable. And that is going to be it in terms of the content for this lecture. Now, there is this interesting little sub line describing femtochemistry, and if you're compelled to elaborate a little bit on what we've been talking about, please go through this example. But I think we'll leave it here in terms of new content for the chapter. So that's it for chapter 10. We'll pick up with another chapter related to rate, and I'll be talking to you about that soon.